Okay, maybe I can start now. Can you all hear me?
Yes.
I only see 5 people. Have an idea where everybody is? Anyway, okay, I will start. So this is being registered.
Yes.
Okay. Okay, so now we'll start. So we were talking about fields. So mostly we'll talk about field extensions and Galois theory. So I had introduced the characteristic of a field. And I had introduced what is a field extension. Just so if K is a subfield of a field L, then L over K is a field extension. So it's just this word, and the characteristic was that the smallest number, if such a number exists, such that n times 1 is equal to 0, or 0 if there's no positive such number. And it's clear that if L over K is a field extension, then the characteristic of K is equal to that. L, this is just because the element 1 will always be an element in the smallest field already. And so n times 1 is still in K. And so whether that is 0 or not does not depend on the bigger field. OK, so now we can start. The first thing is we want to introduce an important invariant of a field extension, which is the degree. The point is that if L over K is a field extension, then L is in a natural way a K vector space, and the degree would be the dimension of this K vector space. So it's the following remark. That L over K be a field extension, then obviously by definition we have that L with the addition is an abelian group. No, that's part of being a field. And if we restrict the multiplication so in L from L times L to K times L gives us a scalar multiplication, gives scalar multiplication. As I said, from K times L to L, which sends an element A in K and an element X in L. So AX, just the product in L. And we have the distributive laws. That if, for instance, that if I have A plus B, where A and B are from K, times X is AX plus BX, it's just a special case of the distributive law in L, in the field L, and A times X plus Y, where now A is in K, and x and y are in L is ax plus ay. Again, it's just a restriction of the usual distributive law in L. And we also have the associative law. If I take A times B times x, where x is again an element from L and A and B are from K, this is the same as if we first multiply A and B in K and then multiply it with x. This is again just a restriction of the distributive law in the field L. And finally, we have 1 times x is equal to x for all x in L. Okay, so what does that? So these are precisely the axioms of a K-vector space. So that is, L is a K-vector space. And so a natural invariant, as I said, that we can consider for L, for the field extension K over L, is the dimension of this K-vector space. So definition. The degree which I denote L over K, like the index of the group, L over K of the field extension is the dimension of L as K-vector space. And this is including the possibility that this dimension L over K can also be infinite. So the extension is called finite if the degree is finite. So L over K is called a finite extension if L over K is finite. Okay, so this is this definition. In particular, it is clear that if the degree of the field extension is 1, then L is just equal to K. So if L over K is a field extension, and the degree of L over K is equal to 1, then L is just K. This is because now L is a one-dimensional K-vector space, so any non-zero element will be a basis. So for instance, the element 1 in K will be a basis as a K-vector space. And so then it's just K. So now we want to see, if we iterate field extensions, what happens to the degree of the field extension. So for this, I introduce the word of intermediate field, which we will also use often later. So intermediate field of a field extension is just a field which lies between the bigger and the smaller field. So if F over L and L over K are field extensions, we say that L is an intermediate field of the extension F over K. Okay, because obviously, if this is a field extension and this is a field extension, then also this is a field extension. It just means that K is a subfield of L, L is a subfield of F. Okay. So this is this definition. So now, as I said, we want to see how this degree behaves for intermediate fields. And it's very simple. If you do one field extension after the other, the degree multiplies. So let say L over K and F over L be field extensions. Then the degree of the biggest field over the smallest is equal to the product of F over L times L over K. As also notation suggests, it it multiplies like this. Okay, and this is, I mean, in theory, these numbers can be infinite, so we use the convention that n times infinite is equal to infinite. N is equal to infinite for all n positive integers. So, okay, so anyway, this only has substance if if none of the numbers is infinite, and then it just says the numbers multiply. So first, what I write here, if something is infinite, this is in some sense trivial. So if say F over L or L over K are not finite, then clearly F over K is not finite. So if you have here infinitely many linear independent elements in L over K, then they are also linear independent here, and in the same way here. And it's also easy to see the other way around, that if F over K is infinite, then one of the two must be infinite. Also converse is easy. So the real thing that we want to have to show is what happens for finite extensions. So assume that so say L over K and F over L are finite extensions. So let's just, so that means this is a finite, L is a finite dimensional K vector space, F is a finite dimensional L vector space, we can choose bases. So let, say, x1 to x, which, how do you want to number them, n be a basis of L as a K vector space, and y1 to, say, ym a basis of F as an L vector space. Now, in some sense, if you just look at the statement, it should be clear how we want to go about the proof. We want to make a basis of F over K. And the most natural thing we could imagine here is that we take all the products of xi and yj. And if these form a basis, then the dimension is precisely of F as a K vector space would be m times n, and that would prove it. So the claim is if I take the set of all xi, yj from for y equal 1 to n and j from 1 to m, okay, these form a basis f over k as a k vector space. Okay, and so one just checks it. So we have to show they generate and they are linearly independent. So I take element y in F. I have to write it as a linear combination. So first, as these yi form a k vector space, I can write it as a linear combination of the yi with coefficients in L. Then I can write y equal to sum I equals 1 to m bj, or this I want to call j, bj, yj, where the bj are elements in L. And now we use that the xi are a basis of L as a k vector space, so we can express the bi instead of the xi. So for all j, I can write bj is equal to sum I aij. Do you want to write this? Or maybe aij xi, where the bj, where the aij are elements in K. So thus clearly we have that our given y can be written as the sum for j. So this was I from 1 to n, j from 1 to m, sum I from 1 to n, aij xi yj. Okay, so this shows they generate. And now they are, I also have to show they are linearly independent. And basically, one does the same argument backwards. Okay. So if we have a linear combination of these which are 0, so if sum over I and j, aij xi yj is equal to 0, then first we use that the yj are, so where the aij are elements in K. Then we first use the fact that the yj are linear independent to see that it follows that all of these must be 0, as the yj are linearly independent. Over L, we get for all j from 1 to m, we have that sum I aij xi is equal to 0. And now, obviously, we use that the xi are linearly independent over k. It follows that all aij are 0. Okay, so this is was a very simple proof. One just tries the obvious thing, and it just works without further thought, and one just applies the definition. So, but this degree theorem is still very useful. One kind of wants to use it all the time because you somehow can, it's a very useful invariant, and to know how it behaves if you iterate field extension obviously is extremely useful and helps in many proofs. There are some simple consequences. For instance, it's obviously it's clear corollary. If I have a field extension, finite field extension, and L is intermediate field, then we must have that the degree, say, however I wanted to, for instance, the degree of L over K divides of F over K. So in particular, for instance, in particular, if this degree of this field extension happens to be a prime number, there can be no non-trivial intermediate field, or the intermediate fields can only be F or K. So if the degree of the field extension F over K is a prime number, the only intermediate fields of this field extension are F and K. Okay? So this, anyway, this is kind of useful. We know there are some restrictions on the possible field extensions just from this. So we will be interested in this course in algebraic extensions. So an algebraic field extension is one where the elements in the bigger field all are zeros of polynomials with coefficients in the smaller field. And making such extensions and studying them has a lot to do with trying to solve polynomial equations. And so let me introduce this. These are algebraic extensions. So as I said, an extension L over K will be called algebraic if every element of the bigger field L is a zero of a polynomial with coefficients in the smaller field K. So definition. So first, let L over K be a field extension. First, I call an element algebraic if it's the zero of a non-zero polynomial. So an element, say A in L, is called algebraic over K if there's a polynomial say F, coefficients in the smaller field, which is not just a zero polynomial, such that it vanishes at A. Okay, so this is an algebraic extension. Otherwise, F will be called transcendental. A is called transcendental over K. So I call the field L algebraic over K if every element of L is algebraic over K. L over K is an algebraic extension if every element A in L is algebraic over K. At this very moment, we don't even know whether there are non-trivial such extensions, but one could hope, and we'll see in a moment that there are many. Let me first give some examples of algebraic and transcendental elements. So, example, for instance, square root of 2 algebraic over K. It's a 0 of the polynomial x squared minus 1 minus 2. And I, so the complex unit in C, is algebraic over K. Polynomial x squared plus 1 over Q, I want it in this. Okay. An example of transcendental elements is something like E. Pi are transcendental. They are both quite difficult to prove. They were proven, I think, for E at the end of the 19th century, for pi in the beginning of the 20th century, and this was considered a major achievement. On the other hand, one knows that one can prove that the algebraic elements, say, in the real numbers are countable, whereas the real numbers altogether are uncountable. So almost all real numbers would be transcendental over Q, but it's slightly more difficult to find a concrete one. Okay, and here are some interesting examples which are not so easy to see. So we are anyway only interested in the algebraic things. So now what we can do is we can take an element in some bigger field which is algebraic over K and add it to K and hope and maybe add several such elements and see what we get, in particular whether we get an algebraic extension this way. So definition. So let F over K be a field extension. Take some elements A1 to AN elements in F. So the extension of K generated by A1 to AN, so which is denoted K A1 to AN, like this with round brackets, is the intersection of all subfields of F which contain both K and A1 to AN. say, L of F which contain K and A1 to AN. So it's clear that if I intersect two subfields of a field, I mean, the intersection will again be a subfield. And this also is true if we intersect possibly infinitely many subfields of a field. So this intersection of all subfields which contain K and A1 to AN will itself be a subfield of F, and it will contain K and A1 to AN. It will be the smallest subfield with this property. So by definition, this is the smallest subfield of F containing K and A1 to AN. So this is this this extension generated by finitely many elements, A1 to N. So what will be particularly interesting for us is the simplest case of this, namely that we only add one algebraic element. This will be called a simple algebraic extension. The reason why it is particularly interesting for us is that first, you will see that these field extensions can be described very well and very explicitly, and one can understand them very well. So that's always good. And the second is that with a small extra assumption, all algebraic extensions are so-called simple algebraic extensions, so just obtained by adding one algebraic element. So that, one is in the best of all things. So one has, first, these are the good ones, and secondly, they are also all that there are. So let me define it, definition. If A in, say we assume still we have our F, in F is algebraic, for K is an extension. Algebraic, then Ka over K, this extension, is called a simple algebraic extension. And as I said, we will see that these extensions are easy to understand, first, and secondly, that under suitable conditions, all algebraic extensions are simple algebraic extensions. So therefore, they are very important. They are somehow, it's enough to really understand them. But anyway. So now we have to understand, now we have to find out how to understand such a simple algebraic extension. And the simple algebraic extension can be understood in terms of its minimal polynomial. So this will be an irreducible polynomial with coefficients in K such that A is a zero of it. So in terms of this polynomial, we can explicitly describe this field extension. So let me introduce this. So first, we actually want this polynomial to be monic. So a polynomial F, coefficients in K is monic if its leading coefficient is 1. So that means, if it has degree n, it starts with x to the n, and something times x to the n minus 1, and so on. So this is just also a way to normalize the polynomials. So note, it's clear that for f a non-zero polynomial, there is a unique monic polynomial which generates the same ideal. So G in Kx such that the ideal generated by f, obviously in Kx, is equal to the ideal generated by G. And obviously this monic polynomial is just obtained as follows. We take f and we divide it by its leading coefficient. Then it becomes monic. And we have just divided by a unit in the polynomial ring. And so they generate the same ideal. Okay. So this is this. So now we want to describe this minimal polynomial. There are two equivalent ways how one can define it. We start with a, in some sense, more complicated definition, but which is often more useful. Namely, so let A in L, so L over K, here we had F. So F over K was a field extension, A was an element in F, so let A in F algebraic over K. So let's look at the evaluation homomorphism from the X. So F, which sends any polynomial G to evaluate it at A. This certainly goes from Kx to F, because A is in F. If I just replace the variable x by A, and so I get some polynomial expression in A with coefficients in K, this will be some element. This will be some element in F. And it's a homomorphism. And by definition, we note that A is algebraic. I mean, the condition that A is algebraic is equivalent to the evaluation homomorphism, kernel of the evaluation homomorphism, different from 0. Because by definition, A being algebraic means there's a non-zero polynomial such that if I put A into the polynomial, I get 0, which is precisely this statement. So as we know that Kx is a principal ideal domain, so this kernel will be generated by one, by unique, has one generator. So thus it follows there exists a unique monic polynomial that you note FA Kx such that this kernel of the elevation homomorphism is ideal generated by FA. So the kernel is an ideal. So it's a principal ideal. It's generated by some element G, by some polynomial G, and then I divide it by its leading coefficient to get a monic polynomial, and that's unique. Okay, so this thing I call the minimal polynomial of A. FA is called the minimal polynomial of A over K. Okay, so we have defined this in this way. It's slightly intricate. We take the kernel of the evaluation morphism, and we take the unique generator of this kernel of the evaluation homomorphism at A. There's another way how we can describe the same thing, and this is certainly useful, and that's the way how one checks that something is the minimal polynomial. Namely, we can say that this minimal polynomial is the unique, irreducible monic polynomial with coefficients in K, such that evaluated at A, it gives 0. So instead of asking this thing to be a generator of the kernel of the evaluation homomorphism, we ask it to be irreducible. Well, and vanishing at A. And it's kind of obvious that these two should be equivalent, but now let me carry this out. So this is the following proposition. So I have again, let F A in F algebraic over K. So the minimal polynomial of A over K is the unique irreducible polynomial, irreducible monic polynomial f in Kx with f of A is equal to 0. Okay, we have to see that this is equivalent to this other definition. Proof. So we have, for instance, to show that this FA, which we defined as the minimal polynomial, the generator of the kernel of the evaluation homomorphism at A, is irreducible. So and this follows quite easily from the fact that it generates this idea. So assume FA equal to G H, where G and H are polynomials. X we have to show that one of them is a unit. G is an element in K star, or H is an element in K star. So we know FA vanishes at A, so 0 is equal to FA of A is equal to G of A times H of A. So, as we are in a field, if a product of two things is 0, then one of them must be 0. So it follows that G of A is equal to 0, or H of A is equal to 0. So if, say, G of A is equal to 0, then it means that G is in the kernel of the evaluation homomorphism at A, so therefore G is in the ideal generated by FA. So thus, we can write G is equal to L times FA for L in Kx. And so we get that FA is equal to G times H is equal to, what is it, G times to L times H times FA. FA is a non-zero polynomial. We are in an integral domain, so it follows that L times H is equal to 1. And so it means that both L and H are non-zero constants. So in particular, our H is in K star. Okay, so this shows that FA is indeed irreducible. So now, conversely, if I have a monic irreducible polynomial which vanishes at A, we have to show it's equal to our FA. Conversely, X monic irreducible. With G of A is equal to 0. So, as G of A equal to 0, it follows, so we ought to show that G is equal to FA. So, as G of A is equal to 0, it follows that G is an element in FA, because after all, FA generates the ideal of all polynomials which vanish at A. Thus, we are again in the same situation. We can write G equal to L times FA, L some polynomial. But we know that G is irreducible, so L must be a constant, non-zero constant. So as irreducible, follows that L is an element in K star. But now both G and FA are monic. So here the leading coefficient, one can see the leading coefficient of G is L times the leading coefficient of FA. So this can only be if L is equal to 1. We get L is equal to 1, equal to FA. Okay, so this was simple. So let's look at at least one example. So we had seen that if P is a prime bundle, M is some positive integer, then whatever. Then by Eisenstein criterion, we have that x to the m minus p is irreducible. So 1, 0 of this polynomial in an extension of Q is the mth root of P. So thus x to the m minus P is the minimal polynomial of mth root of P. Okay, so it's in concrete cases quite simple. So now I claimed before that we use this minimal polynomial to describe the simple algebraic extensions. So I have to now deliver on that. So I have to tell you describe a simple algebraic extension in terms of the minimal polynomial. And in some sense, maybe it shouldn't come as a surprise that, so the minimal polynomial is some irreducible polynomial. So one could hope that one takes, if f is the minimal polynomial of some element a over k, then one way how one can make a field which out of this minimal polynomial is to take kx divided by the ideal generated by f. This will be a field because f is irreducible, and therefore in a PID it generates a maximal ideal, and so the quotient kx divided by the ideal generated by f is a field. And then we have to see that this will be actually isomorphic to Ka. So it's the following. So I have the following theorem. Let A f be algebraic over K. With minimal polynomial Fa, and we write m for its degree. Then we have the following. First, the field Ka, so which you obtain by adding the simple algebraic extension generated by A of K is isomorphic to Kx modulo the ideal generated by FA. And the rest is a consequence. So the degree of the field extension is equal to the degree of the minimal polynomial. And in fact, we can say what the basis is. And if I take 1, A, and so on until A to the m minus 1 are a basis. Of Ka as K vector space. And if you think a little bit more about it, it also tells you precisely how to compute in this field. So let's first prove this. So I use this definition with the evaluation homomorphism. So if I have the evaluation homomorphism from Kx, in a priori it goes to F. But what do? You take a polynomial and you replace x by a. So the coefficients of the polynomial are in k. So you get a polynomial in a with coefficients in k. So some combination of some sums and products of powers of a's and elements in k's. So any field that contains k and a will contain all such elements. So therefore, this evaluation homomorphism actually goes to Ka. So actually has image in Ka. Because f is equal to some bi a to the I, x to the I, if, so maybe I call it G, is a polynomial, then G of A equal to some bi a to the I is certainly in Ka. If I have a field which contains the bi and contains A, then it contains also such a linear combination. Whatever, for any finite sum. So, okay, so this actually goes to Ka, and it's a ring homomorphism. So this send G to Ga is a ring homomorphism. So I have a homomorphism from Kx to Ka, which is ring homomorphism, and I know its kernel. The ideal generated by Fa. So in order to prove this isomorphism, it's enough to show that the map from Kx to Ka is actually surjective. To show that if A because then the homomorphism theorem says that Ka is isomorphic to this. So let L be the image. We will want to show that it's the whole of Ka. And we know by the homomorphism theorem we know that L is isomorphic to Kx divided by Fa. So as Fa is irreducible, Fa is a maximal ideal. No, because Kx is a PID, principal ideal domain. Therefore, Fa is a maximal ideal. And so thus Kx divided by Fa is indeed a field. So thus L is a subfield of F. And in fact, it's a subfield of F, but we also know it's contained in Ka, so it's a subfield of Ka. And it so obviously K is contained in L as the image of the constant polynomials. A constant polynomial is just sent to itself. And A is the evaluation at A of the polynomial X is also in L. So therefore, we have found a subfield of Ka which contains K and A. But we know that Ka is the smallest subfield of L which contains K of A. So therefore, this must be Ka. So thus L is equal to K. Okay, and so we found this statement, the first part. Now the second statement is we just have to see what it means, what we have shown. And we have shown that this evaluation homomorphism is surjective. And that actually is basically translates directly into the statement of the second part. So just so let me just see. So we have the elevation homomorphism at A from X to Ka surjective. So that means every element of Ka is the evaluation of a polynomial at A. So thus, we can write Ka as the set of all G of A with G Kx. So now, first, now we want to see that we have, so we remember that the degree of the minimum polynomial was m. Now we want to see that we have this basis 1 until a to the m minus 1. So 1, a to the m minus 1 generate Ka over K as K vector space. Well, we have to remember this thing with these polynomials. So if I take an element B in Ka, I can write it as a polynomial evaluated at it. So I can write G, I can write B equal to G of A for some G in Kx. And now, well, now how do we proceed? So we make division with rest by the minimal polynomial to see that B can also be written as whatever R of A for some polynomial of degree smaller than M. And that will give us the statement. So if the degree of G is bigger than M, which is the degree of Fa, we make a division with rest. To find that we can write G is equal to Q times Fa plus R, with Q and R some polynomials, and the degree of R smaller than the degree of Fa. And then obviously G of A, so our B was G of A, which is Q of A times Fa of A. But this one is 0, so this is 0, plus R of A. So we can write B as R of A as a polynomial like this, of degree smaller than M. So thus, so we get B is equal to R of A. And so if we write R equal to some I equal 0 to M minus 1, some coefficients could be 0, but anyway, Bi x to the I, we get that B is equal to R of A, so sum I equals 0 to M minus 1 Bi A to the I, which lies in the ideal generated by 1, in the vector space generated by 1A and so on until A to the M minus 1. Okay, so this is quite simple. And conversely, we can argue in the same way. If we have to show that these elements are linearly independent, and then if they are not, you would find such a linear combination of them which is 0, which gives us a polynomial of degree smaller than M, which vanishes at A, and which is not possible. So let me carry this out. So assume that 1, A, and so on until A to the M minus 1 are linearly dependent. Then we can write zero is equal to sum I equal 0 to M. Well, maybe I take a bit more space. So then we can write 0 equal to sum I equals 0 to M minus 1 Bi A to I for bi some elements k. But this means, thus if we write a g sum I equals 0 to m minus 1 bi x to the I, we have that a is equal to 0. So so thus P is in the kernel of the relational morphism at A, which is the ideal generated by FA. And this is actually, this is impossible because the degree of FA is bigger than this. I mean, it's impossible unless G was a zero polynomial, in which case, which precisely means, so actually here one would not assume it's independent, just to assume we have such a linear combination, and then it follows that all the bi are equal to 0. So this is impossible unless G is equal to 0. That means 0, and so on until bm minus 1 are all 0. Okay, and so they are linearly independent. Okay, so maybe just one remark. How does this, what does this have to do with computing in how does one compute in such a field? Now, how do we add and multiply elements? That's pretty clear because we have precisely, it's explained here. As a ring, Ka is isomorphic to this quotient ring. So one can make it concrete by just saying the following remark. So let Ka be a simple algebraic extension with minimal polynomial Fa, which I write sum I equals 0 to m bi x to the I, then how do we compute? Well, we know as a vector space is generated by these elements, so we can write then Fa, then Ka can be written as the set of all sum I equals 0 to m minus 1 I a to the I with I and k. So these are all distinct elements. For addition, just as for polynomials, you just sum them component-wise. You have two such polynomials in A, you just sum the coefficients. And the product multiplication is also, the claim was this was just the quotient of the polynomial ring by the idea generated by F. So you also multiply them as polynomials in A. So, the usual rule that we multiply them according to the rule of polynomials, as if the A was the X. But then, if we have some power which is higher than M, we can reduce it by remembering that FA is 0 in this. So, together with the rule, that if I have a power of A which is at least M, this is just minus some I equal 0 to M minus 1 bi A to the I. No? Because which is besides the statement that F, I should say here, maybe I should write it better, because it's a monic polynomial, so it's x to the m plus some I equal 0 to m minus 1 bi x to the I. If I put A into it and bring the this on the other side, we get precisely that f of A is equal to 0 is precisely this statement. And so whenever we multiply things out and we encounter some powers which are bigger than m, bigger or equal to m, we apply repeatedly this rule until we get something which is expressed in this form. And so this gives us also the ring structure or the field structure. So just as an example, this gives you the familiar rule how you compute in the complex numbers. So we have seen the minimal polynomial of, say, a complex unit I over the real numbers is x squared plus 1. So thus, C, the complex numbers, can be described as the real numbers to which we add I. So this means that as a vector space over R is just a set of all A plus BI with A and B in K. So this was after this description. And the addition is just component-wise. And the multiplication is by this rule I just explained. Where is it? So addition is just, so maybe you can say it, addition A plus BI plus I. So we just, vector space is A plus C plus B plus I. And the multiplication is more interesting, and let's multiply them. We have here A, C plus, what is it? A, well, maybe I connect these, so, well, whatever, plus A, D, I plus I plus, I made a mistake, plus, I made plus B I squared. And then remember, the minimum polynomial is x squared minus 1. So I squared x squared plus 1, so I squared is minus 1. And so this gives us the familiar rule AC minus BD plus AD minus plus BC times I. So the rule that one learns in complex analysis or wherever for addition, for how you compute in the complex numbers, is just the rules which come from the fact that the minimal polynomial of I is x squared plus 1. Okay. Wondering. Now I want to talk about splitting fields. So I just will briefly introduce it. So the idea is that we want, when we have a field and we have a polynomial with coefficients in the field, we want to find an extension of the original field such that f, our polynomial, can be written as a product of linear factors. We want to see that such things always exist. So let K be a field, F polynomial with coefficients x, not constant. So we want to find an extension L over K such that F splits over L into linear factors. That means I can write F is equal to, say, some number B times x minus A1 and so on times x minus AN, where B and A1 to AN are all elements in this field L. Okay, and we want to find that. So in order to find such a thing, one should first find a field. So one can see here, if this is supposed to be the case, then F has to have these n zeros, A1 to AN. So let's be a little bit less ambitious to begin with. We first want to find an extension of K such that F has 1 0 in it. So it's the following theorem. Stop. Let F in Kx there exists a simple algebraic extension say L over K, whose degree is F is the same as F, so L over K F such that F has a 0. That F has a 0. So note we are not given any other field. We are only given K and F. So we somehow have to construct our field L out of F. And we have only one way how we can do it, which we have just used a moment ago. We can take Kx, polynomial in Kx, divide by the ideal generated by F. And we hope that this will do it. So let's see. So we use F to construct L. So again, we have the same story. F is irreducible. X is a principal ideal domain. So thus, we have that L, which I defined to be Kx modulo the ideal generated by F, is a field. We've constructed our field, and I can say that K is contained in F, namely as just the constant polynomials. So K as constant polynomials. We had seen before we had considered this, that in this case we get a field extension that, at least if we identify K with the image of the constant polynomials, which are isomorphic, then K is contained in L. Now, the only thing that we still have to see, and which is maybe a little bit less obvious, is that F, our original polynomial F, should have a 0 in L. And now we don't really see what the 0 should be. But if one thinks a bit harder, it has in a tautological way a 0. If we take the class of X in this quotient, if we put this class of X into F, we get the class of F, which is 0. And so let me write this down. So F has a 0 in L, namely the class of X. So I mean the class of X in Kx modulo F. Why is that? Well, let's just write it down. Where is it? So we write F equals sum I equals 0 to whatever n ai x to the I. Then we know the class of F is 0. No? Because we have divided by F. So what does it mean? So the class of F is the sum I equals 0 to n ai x to the I. But we have made this, so we have the constant polynomials. So maybe I should say a bit more here. So we have pi from Kx to Kx modulo F, the canonical projection, which is a ring homomorphism. And we know it is injective on K, and we identified K with its image. So that it's so that's the ring homomorphism means that we can pull the sum out, and we can separate this product in the class of AI and the class of X to the I. with our identification, the class of AI is just AI. So this is the same, sum I equals 0, n AI x to the I, which is the same as sum I equals 0 to n AI x to the I. And so we see, indeed, the class of x is a 0. So it's a bit, so definition in this situation, we say L is obtained from F from K by formally adjoining say a root of F. So it's a bit strange because we have kind of created this out of nothing, and the 0 is obtained in this tautological way, but it is okay. In this way, we know we always find a field extension in which our polynomial has a 0. And then it's clear how one wants to proceed to go to the splitting field. We would divide by x minus this 0, get a polynomial of lower degree, and we can find a further extension where that has a 0, and we go on until it splits into linear factors. But we'll see that next time. So maybe I stop here. Are there questions or comments? Okay, that doesn't seem to be the case. So then, well, we'll see each other on Thursday this week. And I think tomorrow you're going to see the director, no? Okay, so have a nice evening, and we see each other on Thursday.